Hey kids, time to move on to infinite series, right? We started out with sequences, which is just a list of numbers. And we looked at the patterns of the behavior as you take those terms to infinity. Then we turned them into series. Series was a sum of those terms. But we looked at finite series, and we talked about two famous kinds, right? Arithmetic, where there's a common difference, and geometric, where there's a common ratio. Now we're going to move on to infinite series. And since infinite series indicates summing, the sum of an infinite series, and we're going to focus mostly on geometric today. Geometric series, that's a weird idea. Oh, I just didn't spell that right. Diverges. The idea of a sum, how can I even find a sum if I'm adding forever and ever and ever? How is that possible? So I like to talk about and visualize this house or shed, right? Where I want you to visualize a first term, adding another term, adding, and you're stacking your sum in your house. If you add numbers that are getting infinitesimally small, you could reach a point where the numbers you're adding are so small it never appears to grow, and your sum stays in the house. You reach a boundary. Your sum reaches a boundary, never goes out the house. That's a convergent series. As opposed to a divergent series, I want you to say here's the first term, then you're adding the next one, and your sum is getting bigger and bigger and bigger and bigger and bigger and bigger and bigger, and you bust out the house. That's a divergent series. So I'm going to talk about the formal definition of any series, whether it's convergent or divergent, and then we'll move on to investigating patterns, right? And trying to make some generalizations for certain types of series. And again, today we're going to focus on geometric. So this idea of infinite series, as I said, is super weird. Notice that I'm going to infinity with my sum. So if I was to expand this summation, I would put 1 in for my first term, add the second term, add the third term, add to n maybe, but then I don't stop at n. I keep going forever and ever and ever. It's an infinite series. You are adding terms forever. And what I want to know is, are the numbers I'm adding getting smaller and smaller and smaller, and so small, so infinitesimally small, that my sum reaches a boundary? Again, here's the theory behind this. If the sequence, which is a list of partial sums, so the first two terms, what's that sum? The first 10 terms, what's that sum? If the sequence of those sums converges, so we've already talked about what a sequence looks like that converges, to a number, we call that number the infinite sum, usually indicated with a capital S. Oh my God, what is that? That's what this says. If you have an infinite series and the limit as n the number of terms goes to infinity, right? K is equal to 1 to n. If that limit is a number, you've been doing limits for a long time now. Remember, limits, you can get a number, or you can get an infinity, or you can get it does not exist. If you get a number Then the series converges to that number. If the limit does not exist, or I don't know why I didn't type this, positive or negative infinity, then the series is divergent. So I'm going to show you an example of each one of these. So again, this is all great, very fun, very mathy. So this is the long way to investigate. We're going to do this long way once, and then we're going to try to generalize. So if I ask you to find the first four partial sums, what I mean is, what is the sum after the first term? Well, that's 0.3. What is the sum after the first two terms? 0.3 times 0.0 plus 0.03. What is the sum after the first three terms? 0.3 plus 0.03 plus 0.003. What is the sum after the first four terms? Can you see that the limit of this list, right? The limit of that list is going towards a number, right? 1/3. So as I go to infinity, if I kept going, can you see that? That sum is going to get smaller and smaller and smaller. What about the next one? Can you see what's going to happen there pretty quickly? The sum of the first is 5. The sum of the first two is 15. Now I have a formula to do it, but I can just, these are simple enough to just add, right? Right? I have my formula that is what? 1 something 5 plus, fraction, blah, blah, n over 2, da, 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 da. I don't need it here. What did I do? 15 plus 15 is 30. 30 plus 20 is 50. Can you see what's going to happen here? What is the limit as the number of these values? What is the limit of this sequence? That grows without bound. What about the next one? It's kind of weird. But what is 1/3 minus 1/3? What is 0 and 1/3? What is 1/3 minus 1/3? What is the end behavior? What is the limit as the number of these sums, this list of sums, goes to infinity? There is no describing that end behavior. It doesn't swoosh up, it doesn't swoosh down, and it doesn't approach a number. So this series converges, stays in the house. This one goes out the house, diverges. This one we say diverges as well. Doesn't really bust out the house as much as it just doesn't do either, right? You have a third and then you have a third and then you have 0 and then you have a third and then you have 0 and then you have a third, right? You don't go anywhere. Look at the plot of these terms. And maybe you can see, right? Look at that. What is that end behavior? Right? Crazy. As opposed to, what about that first one? That first one was what? The first term was 1/3, right? No, it was 3/10. Sorry, it was 0.3. It was 3/10. What was the common ratio? Common ratio was 1/10. See what's happening there? Let me slow it down a little bit. Right? Look at those terms. Getting pretty small, right? So, again, we don't really want to go through all that. We would like a shortcut. Please tell me that there is a shorter way to determine convergence. And I will tell you, you don't know why at this point, and you won't know why in a high school class. Any high school class, doesn't matter. Convergent is a series we want. This is, we want convergent series. The minute I know a series diverges, I throw it out. But my convergent series, I kind of really keep with me close to my heart. I want convergence. So I would really like a shorter way to test to see if you give me a series, I don't want to have to make a bunch of partial sums and then investigate it. Well, arithmetic series do not converge. Sorry, arithmetic series, you're out. Right? Does that make sense? An arithmetic series, remember, we found is just, right? That's just a linear, right? That just, it's going to go to positive infinity or negative infinity. Does not converge, right? So that second example, 5 plus 10 plus 15 plus 20, nope, not going to converge. You have a common, so as soon as I recognize that pattern, nope, does not converge. However, a geometric series will converge if and only if that common ratio is strictly less than 1. This goes back to Algebra 2. In function land, if I had a times b to the x, if b was between 0 and 1, right? Then I had a slide towards a horizontal asymptote of 0. If b was equal to 1, right? Meh, flat line. If b was greater than 1, swoosh off to infinity. So a geometric series is not an exponential function, but the behavior is similar. When you add and add and add numbers that are getting smaller and smaller and smaller, not only do the terms approach 0, the sum approaches a bound. So don't, right, think this is what the terms are doing. What is the sum doing? When you are adding, the sum will stay in the house. The sum is growing, but it is growing to a boundary. If and only if that common ratio is strictly less than 1. And as a matter of fact, if you have a convergent geometric series, you can find the sum, which is very difficult to do for non-geometric convergent series, if not impossible. This formula you want to write down and you want to remember it. The infinite sum of a convergent geometric series is the first term divided by 1 minus that common ratio, not the absolute value of either. So I can prove, this is not actually a hard thing to prove either. Look at this expression here. Right? If I'm going to take the limit as n goes to infinity, remember this is, right? Our sequence formula looks like this. Well, as you're going off to infinity, remember this is a number, what does this do? Right? That's going, right? Lard, you're raising r to lard, right? So what's happening if r is less than 1? Right? So for example, if you have if my r is, I don't know, a half, and you keep putting it right to the first, 1/2 squared, 1/2 cubed, 1/2 right to the fourth. This term right here is getting, as the n, right, gets larger and larger and larger, this value gets smaller and smaller and smaller, is approaching 0. So this is a sub 1 times 1, which is just a sub 1 over 1 minus r. Kind of cool. So look at these series. Do they converge? If so, give a sum. This is a clue, probably geometric. If they're asking you for a sum at this point in your math career, even after you're in BC calculus, if somebody's asking you for a sum of a series, it is probably geometric. So are these geometric? You have to recognize the common ratio is a half. The absolute value of a half is strictly less than 1. Therefore, this geometric series will stay, right? The sum will stay in the house. I will converge. This series will converge. Further, since it is a convergent geometric series, the sum is the first term over 1 minus r. What's my first term? First term is when k is equal to 1. So 1/2 to the 0 is 1/2, because it's 1/2 to the 0. I'm sorry, is 1, excuse me. 2 times 1 is 2. So again, think of my house analogy. Since it's a geometric series, I'm going to be adding 2 times 1/4 to the 0, 1/2 to the 0, 2 times 1/2 to the first, 2 times 1/2 squared. And I'm going to be adding all of those numbers. But as I go to infinity, those numbers are going to get infinitesimally small, and I'm adding and adding and adding and adding and adding and adding. But the sum will never get above 4. Little bit more mathematical. You're adding numbers. Your first term, right? Your first term was 2. Then you are adding, but you added a number. The sum's getting smaller. Sum is getting small, right? This is the sum. Sum is, you're still adding, so you're growing, but you're growing to a boundary that will never go above 4. How about the next one? B. Is it geometric? Yes. This is my common ratio. A is out front. 1.5 is 3/2. The absolute value of 3/2 is greater than 1. Therefore, this geometric series will diverge. So when you are adding 1.5, put 1 in here, and you get 1.5 to the 0, which is 1. Then you're going to add 1.5 squared, or to the first, I'm sorry, then 1.5 squared, then 1.5 cubed. You're going to add, you're going to add, you're going to add. This sum busts out the house, does not reach an upper bound. How about the next one? Is it geometric? So this one was geometric, looked at the common ratio. How about this one? Is it geometric? Yes. What's my R? Negative 0.3. What is the absolute value of negative 0.3? 0.3. Is that less than 1? Yes. Therefore, this infinite geometric series will converge. The sum will stay in the house. And further, the infinite sum, I can actually find out what that upper bound is of the sum. What's my first term? Put in 0 for n. Negative 0.3 to the 0 is 1, so that's 4. Over 1 minus negative 0.3. 1 plus 3/10 is 13/10. So what is that, 40 over 13? That's the top of my house. How about the next one? I didn't put it in summation notation. So is it geometric? That's all I got right now. If it's arithmetic, it automatically diverges. If it's geometric, I can find out if it, otherwise I have to just look at those partial sums, and I don't want to do that. So is it geometric? Do I have a common R? Yes, 1/3 divided by 1 is 1/3. 1/9 divided by 1/3 is 1/3. So yes, it's geometric. My R is 1/3. The absolute value of 1/3 is less than 1. Therefore, this infinite geometric series will converge. What's your first term? What's your R? Two-thirds right down here. Cool. Okay. Love the geometric series. If you have a geometric series, it doesn't automatically converge, right? It might swoosh off to positive infinity, bust out the house, like B. But if your common ratio is strictly less than 1, you will converge, and further, you can find the top of the house. Most often, I mean, with any geometric we can, but there's lots of other kinds of series, and we might not be able to find the top of the house, what the number is, right? What that upper bound is, but we can find, we can say that it does converge. That's almost as good. So our strategy so far: does a series converge? If so, give the sum. The first thing I say is it arithmetic? So I look for a common difference. If it is arithmetic, my series diverges, be done with it. If you look at the series and it's geometric, then you find your common ratio, absolute value of, and then you say, is the absolute value of that common ratio strictly less than 1? Then it converges. If it is the common absolute value is equal to 1 or greater than 1, then the series diverges. If yes, though, you have a formula to actually find the infinite sum. First term over 1 minus that common ratio. All right, so that's what we got so far for infinite series.